In the last video, we saw this definition. So the limit of f of x as x approaches c is L, denoted like this, means that given any epsilon greater than 0, there exists a delta greater than 0, such that for all x in some interval, x not equal to c, as long as x minus c is less than delta, then the output f of x minus L is going to be less than epsilon, both in absolute values. So how we use this definition is basically we want to work back for a tolerance level of epsilon. So we start with the tolerance level of epsilon, then we generally find a delta that works. So essentially we're working backwards through the definition. We're starting with the epsilon here, and then we're finding a delta that works. And then we say, well, for any epsilon, the one I just found, there exists this certain delta, and we know it works. Let's look at an example. In fact, let's look at the example we've dealt with a few times already. We have f of x equals x squared plus 2x minus 1. We know that the limit as x goes to 2 of this function f of x is equal to 7. So a question would be, what would delta need to be in the definition if we wanted our epsilon to be 1? So if our epsilon is 1, that means all of the outputs are within 0.1 of, well, in our case, the number 7. So it's saying if we want all of our outputs within 0.1 of the number 7, how close should our inputs be to the value of 2? So let me do this through a graph. So here is my graph of y equals x squared plus 2x minus 1, written in red. And we saw last section that as x gets closer and closer to 2, this graph travels closer and closer to the y value of 7. So we're at the 0.27. That should be no surprise to anyone. So what I've done is I've tried to create a situation, and I hope it works. So we want an epsilon of 0.1. If we want to be within 0.1 of the number 7, that means I need to be in this little section right here. All right? So I need to be within this little section right here. I want all of my outputs to be within this little section. Well, how does that translate down into my inputs? If I let my delta be 0.1, notice that my outputs of my function are not going to be within this green region. All right? But if I start making my delta smaller and smaller and smaller, it's hard to see here. So let's zoom real close into it. So if I let my delta be smaller and smaller and smaller, all of a sudden, when I hit a delta of 0.01, all of the outputs that are within this purple region are also inside this green region. So if I forced delta to be 0.01, then I would know also that my epsilon would be within 0.1. Let me state this again. Let's go back to the beginning in a different way. So what we're saying here is we're given an epsilon greater than 0. In my case, that epsilon is 0.1. So what the definition says is that means we want all of our outputs within this green region here. So how would that translate down here on the x-axis? Well, we need to figure out a delta which is small enough so that within that little bound on the x-axis, all of our outputs within the purple region fall within the green. So if you look at right now, we have delta set at 0.05. There are values of my function that are within the purple region. Purple region is left to right. So there are values of my function within the purple region that are not within the green region. Green region here, it goes up and down. But if I start making my delta smaller and smaller and smaller, then we can see at some point, in my case, if I let my delta be 0.01, then everything that is inside this purple region, left to right, is also within this green region, bottom to top or up and down. So let's again zoom in a little bit more. So you can see all of the outputs that are within my purple are also within my green. So that's the idea. We start with a green region and we say, well, can I draw vertical lines such that within those vertical lines, all of the outputs within the vertical lines are also within these two horizontal lines. Hopefully that makes sense in terms of the graph. So that was sort of a visual of what's going on. Now, the trouble with that is that it's not very precise. And obviously, if you don't get your little sliders right, then it doesn't work very well. Better approach to do these things is algebraically. Now, we saw in our last section that if we had the function g of x equals 3x minus 7, the limit of g of x as x goes to 1 was -4. So instead of trying to do this graphically, let's do this algebraically. What would we need delta to be in the definition if we let epsilon be 0.1 in our definition? So this question asks a simple question that says, we have this function. We already know the limit. So let's find the delta that we would need if I forced my epsilon to be the number 0.1. Now, in terms of the limit, the definition we saw just a couple of slides ago, right? Means that for any epsilon greater than 0, well, we gave one. there exists a delta greater than 0 such that for all x, which basically x minus c within a tolerance level of delta of c, then our output is within a tolerance level of epsilon of our limit. We need to find our delta in the definition so that the output is within 0.1 of -4, given that the input is within delta of our number 1. So here we are. So now we know our epsilon that we want is going to be 0.1. So what we do is we start out by setting my absolute value of g of x needs to be within 0.1 of -4. So g of x, the difference between g of x and -4 in absolute values has to be less than 0.1. Now, we know what our g of x is, so what we can do is we can simply replace g of x with the expression 3x minus 7, and we want that expression to be less than 0.1. So let's clean this up a little bit. We can simplify the insides. So the inside would say 3x. Well, if you do a -7 minus -4, so that's -7 plus 4, you get a 3x plus 3. And then we deal with the absolute values. So if the absolute value of 3x plus 3 needs to be less than -1, then what we can do is we can say that -0.1, excuse me, that the 3x plus 3 has to be between a -0.1 and a positive 0.1. Now for here, we can solve for x. So let's go ahead and solve for x. Let's subtract 3 from both sides. On the left-hand side, you have -3.1 less than 3x less than, if I subtract 3, I get -2.9. And then what can we do? Well, we can divide both or all three sides by 3. If you take -3.1 and you divide that by 3, you get -1.0333. Repeating. If I take -2.9 and divide that by 3, I end up with -0.9666, lots of sixes. Whoops, I just realized something. I messed up way back up here, didn't I? -7 plus 4 is a -3. So before I get any further, that's silliness. I knew I shouldn't have done that way. Knew something was coming out funny there. So I'm going to have to add 3 to both sides. So we end up with 2.9 on that side, 3.1 on that side. We're still going to divide by 3. If you take 2.9 and divide that by 3, you get 0.9, lots of sixes. And if you take 3.1 and divide it by 3, you end up with 1.0 lots of 3s. Now, what's this mean about x? Simply put, let's think about what this means not with respect to x, but with respect to 1. How x is close to 1 here, right? Notice that x has to be really, really close to 1. In fact, if you think about this, let's subtract 1 from all 3 sides. Subtract 1 in the middle, you get x minus 1. Subtract 1 from the left-hand side, you get negative 0.0 and then lots of 3s. If you subtract 1 from the right-hand side, you get 0.0 and lots of 3s. So what's this force x to be in terms of absolute value? Well, force is x minus 1 in absolute value to be within 0.0 and then lots of 3s. Okay? So what's this mean? This means if I set my delta equal to that 0.0 and then lots of 3s, then x minus 1 less than that delta forces me to have my function's output within 0.1 of that limit. So my function's output is within 0.1 of that limit. So as long as I have delta be 0.03333, then my function output is within 0.1. Now, obviously on Moodle or something, I would have you round to maybe 4 decimal places. Hopefully you get the picture, the point.